Excellent. All right. Thank you for the introduction. Let's see what we can do today with part design in an agile world. So I'll start with a brief background of what Ocado does, or Ocado technology. We build and support an end-to-end e-commerce fulfillment and logistics platform for online grocery. And at its core, there's groundbreaking automation robotics. This machine that you see in front of you does the job for Ocado today. It's called the 500 series bot, and it's developed entirely in-house and sets new benchmark for performance, reliability, and speed. As you can probably see, the 500 series is a state-of-the-art industrial equipment. These amazing machines will run sites across the world for our partners for many years to come. The thing is, at Ocado technology, the state-of-the-art is not where our thinking stops. So the demand for grocery e-commerce have forced us to push the envelope for almost 20 years. And I'm here to tell you about how we unlock something completely new. This is the next generation robotics for Ocado technology. It's called the 600 series, if you wouldn't guess. It's designed to perform the, I got a pop-up thing here. There we go. It's designed to perform the exact same thing as the previous generation, but doing so at a much lower cost. And we're doing this by a radical new approach to lightweight. So that's the fundamental idea of the 600 series. While what I'm actually here to talk to you about today is the cube that you see in here. And if you recognize Onshape, you recognize that this cube happens to be designed on Onshape. And it's actually not possible to design an Onshape with traditional methods. So you need to rethink how you actually design a cube in Onshape, or at least we had to. And I'm gonna make the daring move to teach you a little bit how we do it, how we design a cube in Onshape. The 600 series robot consists of over 400 3D printed parts. They're printed in nylon with a part bed fusion technology. And as you've seen, we have thousands of these robots in each warehouse. Knowing a little bit about additive, you might know that it's got no economy of scale. So hearing these numbers, you might naturally ask, why would we even start down the path of additive for making our robots? Don't seem to make sense. Because what you've learned, or at least what I got taught in engineering classes, was that you're best off to avoid complexity. You want to make sure that you simplify the designs anytime you can, anytime you're able to just simplify or reduce complexity. That change is actually really difficult. So you got long lead times of components. You want to lock down your design and make sure that you can use that for 10 years or something like that. And then stakeholders implications everywhere when you try and change anything. So just don't change things, right? You've probably seen this graph before. It's quite traditional when you're talking about AM versus traditional manufacturing. So you got cost on the y-axis, or cost per part, and number of parts on the x-axis, where orange is the traditional manufacturing method and blue is for additive manufacturing. And two things are actually really interesting about this graph when you start to actually think about it from an engineering cost point of view, or design point of view. The height of the blue line only depends on the mass of the part itself. It's got no other input. Essentially, it's the mass of the parts. Essentially, the mass of the part is equal to the cost of the part. And nothing else really matters to the cost of the part in AM. You can make it as complex as you want. It's got no impact on cost. So mass equals the cost of the part, AM part. And the second really interesting thing is that if you never really see this part of the graph. So if you make a completely new part in a traditional manufacturing method, you have to go back all the way up the cost curve. You have to restart. It's essentially item 1 again. Whereas for AM, the mass equals the cost, so you're just restarting at the same cost. Thinking about AM from this perspective, all of a sudden we turn the greatest enemy of AM into its virtue. So for additive, making really complex parts is desirable, and it's also desirable to change it really often. Kind of backwards is what I take from that first time I thought about it, but it's quite fun what you can do about it. So let's start looking at complexity. Well, complexity, we actually want complexity for the sake of being really lightweight, right? Remember, mass equals cost for the parts that we make. So turning complexity into lightweight, how can we do that? I know 2 ways. The first is obviously topology optimization. So you take a part and you let an algorithm just shave away a little bit at a time. From the material of the part, which is adding the least of the stiffness to the part itself. At some point, you've reached the desirable optimum for stiffness, weight, and strength. You tell it what to do, and you get a new part out. This is really cool. Yeah. So this is what it actually looks like when you see this part in Onshape. Topology optimization is super cool, but I'm not here to talk about topology optimization. That's not what I'm here for. I'm here for part design. There is something else with this part that makes it lightweight from a pure systems perspective. The part itself performs more than one function. It doesn't do only one thing, it does many things. Its primary function is obviously being a structural part of the chassis of the bot, but it also houses other components and plays a key part in enabling multiple functionalities across the whole bot in that same part. For instance, it's if you need a sensor and a bracket for that sensor to hold it in place, what we do is just that we make that sensor bracket integral to the part itself. So you got loads of those on these things. You add complexity to the part at no additional cost. Now, topology optimization, this part that you're seeing in front of you, the final part, that's not actually the thing that the mechanical engineers are working on in Onshape CAD. This is the output of an algorithm. So this is actually what it looks like, or sort of. The transparent green is actually representing a constraint for the algorithm. And we're back where we started on our cube. This is actually the part in Onshape that our CAD engineers or mechanical engineers are actually seeing and working on and designing. So why is this not possible to design in Onshape CAD? I'll tell you why. You take a traditional part, you have one part, and this one part has got one function. It's meant to do one thing, typically, simplify, right? In order to design this one part, you need many features, typically. Something like this is very typical when you design a part in Onshape, or any CAD software for that matter. While if you want the one part to perform many functions, you quite quickly get into a cascade of features, and it builds up really fast. It's just creeping up when you want to make an additional bracket here and a structural part here and whatnot. Same part, it's just creeping up way faster than you think, to the point where it's ending up being impossible to design this in CAD. It's just too much for the computation engine to deal with. So we ended up parts that took more than 2 minutes to compute or to regenerate when you made changes to them. You could get sick and tired of waiting quite quickly. So especially if you just want to change the size of the hole, right? Want to change 4.4 to 4.5, and then you've got 2 minutes waiting. So for a single part, complexity is cheap. You actually want huge complexity here because mass equals cost, but not really for the AWS servers. So that's a whole other story there, right? So what can we do about this as a mechanical engineer? We need to rethink this somehow. So what we can do is learn from software engineers. They work on something that's called refactoring a lot. If you've never heard about it, take the opportunity to just Google it, but it's essentially restructuring code to make it a single source of truth. And refactoring of an Onshape part studio is actually required for you to be able to make these type of parts. Things like reorganizing the feature list just to make sure to remove unnecessary features, remove dependencies where you draw a feature on top of a previous geometry. It's computationally heavy to figure out what the next thing does based on the previous one. You can work a lot in Onshape with removing derives and making sure that you remove relationships where you don't need them. Onshape, power user, and everyone else, just start using feature script. You can use one feature to perform multiple things at once more efficiently. So a huge benefit with that one. And obviously variable studios, so you pull out variables that you have, make sure that things are self-referencing. So that's part of making a single source of truth as well. This is nothing new. Starting to be bored now and wondering what am I talking about? You already know these principles. It's the best principles in designing parametric, right? And best practices in Onshape. And if you do get into the habit of restructuring your code and refactoring it and working with it, you can get really far with this. We can do this. This is nothing really weird. But change. We also want change, right? What do we do now? Well, change is possible. So what's the hardest thing about change? Constant change and constant cost creep, scope creep. Oh, damn. So this is the part we started the journey on. What has happened since? Well, some manager told you that we needed more functions, obviously, because cost is, or mass is cost. So we need to hold on to some bearings on the thing. We need to be able to jig it, and we obviously need to glue it. And if we do all these things, we obviously need to measure it. And we got to put some wire routing on it. We need a way of handling adhesives, stiffen up the chassis while we're at it, because some things needed that. And obviously, if you print it all in AM, why not put a bunch of text on it? So you got things like serial numbers, feature tags, and just general user information. Put the thing here with an arrow. Oh, damn. Mechanical engineer sigh. And well, we just get back to more refactoring. Remember this slide. How bad could this be? Well, we've been doing these things for a while for Part Studio, and it is adding up fast. It's adding up to the point where we have single part studios that have the equivalent of 1,300 features in the Part Studio. Those features are all necessary to design one single cuboid part, this green part you see in here. Well, not really that one, but about 2 years later in design. The Onshape user guides tell you no more than 250 features in Part Studio, and we obviously need to do something differently. So what do we do? this is called, or at least something we call, I don't know if it's a general thing, I've been Googling it, but haven't found anything. We call it Boolean Modeling architecture. And in short, it's just taking one part and Booleaning the operation with the second part in order to make the final part. If you know Parasolid, basically what it does under the hood. It's nothing new, but the way that Onshape is set up and the way that we can take advantage of it in Onshape is what's making this possible. And this is what I want to show you today. So we have, as I mentioned, the green part you see, there's been about 2 years of development work on that specific green part since that picture. I would have wanted nothing else than to be able to go through the real part with you. There's got to have to be some other time when the intellectual property concern is reduced. So instead, I'll show you the method of doing this directly on a dummy part. So this blue part is our dummy part. We got 4 threaded holes. I'm not sure if you can actually see my cursor here on the left-hand side. That's got some complex internal features, and then another complex channel-like groove on the right with 4 identical protruding seats that got internal feature channels. That's that section that I mentioned.
We can see your cursor, by the way.
You could not.
We could. We could. Yes.
Excellent. Yeah. Good to know. I can point things out. So especially the threaded features, these ones in here, they're a little bit heavy in Onshape. It's using someone's feature script. It's typically heavy in a Parasolid generation anyway. This part studio takes about half a minute to compute or recompute the feature list. Not the end of the world, but if you need to do work in it multiple times a day, every day, it gets tiring. So what do we do? Well, let's start off with what we call atoms. These are fundamental shapes that we want to use in the actual part. And when thinking about this, you can think about atoms in both a negative shape or a positive shape or an inverse of the shape that you want. So the orange atom here, it's actually the inverse of the hole that we wanted in our final part. And that's basically what it looks like in the part studio. Interestingly, with atoms, you can make them super complicated using every trick in Onshape and all the power features and heavy features and everything. You can go nuts on atoms. So as I mentioned, this orange one uses a thread feature script. So it's a fully designed feature thread. It's quite heavy to compute this tiny little thing. I think it's an M4 thread or something like that. 6 seconds of computation time. So and then we basically call this shape using derive, excellent tool in Onshape, and just booleaning it from the previous body. So it's a Boolean subtract. So we cut that out of the final shape essentially. Interestingly, there's another software analogy here. These are effectively callable functions in the software design, but we use them in part studio design or a part design. And if there's atoms, there's got to be molecules. So this cavity here is also made from an inverse shape. And this is basically what the molecule looks like. I just flipped it upside down on screen here so you can see what's happening in it. It's got some really complex helical shapes within it and some conical thing. So atoms make up molecules, and it's basically a higher level function that you call with the previous function using the software analogy of callable functions. Here we're combining the atoms in another part studio to make the molecule, which is then actually the inverse shape, and then we're working by subtraction of the positive atom to get the final molecule, right? it's just more steps in creating the final Boolean. So to make the final part, we just start combining all these things, right? We combine all the atoms of the molecules. And if you remember, we had about 25 seconds of computation time of the final part studio before starting this refactoring. Now it takes about half a second to compute completely. It's 45 times faster. If you need to do work in this part studio every day, every time, because you want change, you want to continuously change your design, all of a sudden that makes a huge difference in actually being able to even make the changes you want to do. All right, so to conclude a bit, not only is this incredibly fast to compute, as you just seen, all the aspects of this design is fundamentally single source of truth. If you want to change the size of this thing, just change the size of it and update everywhere. So you can make the change in one place and just push the updates to all the parts that you want to use. We reuse these atoms for multiple places and multiple end parts or end use parts on the robot, because you probably use an M4 screw elsewhere. So you just throw that in where you need an M4 screw. And then we obviously have version control derives, the Boolean features that create this. Interestingly, these are incredibly stable features. Fundamentally, they just create a Boolean difference. So it's super fast and super stable as well. Mainly things like edge IDs and point IDs and stuff like that is under the hood in the parasolid generation, which makes just way more stable. Change a lot easier because you know that your callable function is always going to generate a good result. Interestingly, if you take the combination of the Boolean and derive, these features are also independent of the order of operation. So you can drag and drop one feature as in the screw in relation to the molecule. You can change the order of those in the final part studio without actually affecting the output of the part at all. It's going to be the same thing either way, independent of which order you do the Booleans. You wouldn't typically do that in a normal feature tree in a parasolid generator. You'd break a lot of things quite quickly if you remove a feature. And last but not least, it's completely set up for Agile. So it's collaborative in nature. Every single feature is actually something that everyone can go in and edit, both atoms and molecules and the final part all at the same time, and everything still works. It's sort of magical. Only with rethinking part design for an Agile world, we can truly unlock the power of additive. That's my quick update on Boolean modeling architecture. Any questions?
Are there any questions? Thank you very much, Dr. Johannison. That was fascinating, and if a little sobering to hear the challenges you're having with Onshape. But it's very interesting approaches that you're taking to work with Onshape and get results in a faster way. Jordan is asking, have you tried this approach with patterning?
Patterns work perfectly for this, but typically you want to do fewer Booleans. I'm trying to figure out my view here. I'm sorry. Typically you want to do fewer Booleans, so you actually want to you want to derive the patterned thing into your final thing, but it works perfectly well.
Excellent. And how do you handle version control and release management using these features?
So for the atoms and the molecules, we only use version management. Typically, we actually pull out, as I mentioned, we use the atoms in a lot of places, not only for a single purpose. So we run version control for those, and typically atoms and molecules are in separate and separate part studios. Separate documents. So anytime we need to derive something into our end use part for an atom, we use it's naturally versioned, right? Whereas the only things we release are the final parts. But seems to have worked for us. You can probably release managed atoms and molecules as well.
But it sort of makes sense, right? Using versions in a very sort of software-like way to have the sort of versions of the functions, if you like, the versions of the functions you call in, and then you're using releases for the sort of engineering part of the process.
Exactly.
Question here from Matt in the channel: how are you tracking the performance of your robots in the world, and then using that data to improve your designs?
We do that a lot, but the 600 series is not yet in the real world. We do a lot of in-house testing currently. That's where we're at in the design phase. There's a huge amount of data generation from the bots in the world, just not that 600 series is there yet.
That's the 500 series then. That's in.
Yeah.
I realised that I haven't been sharing my video. It's very rude of me. I'm just taking a look through the chat channel here to see whether there's any other questions in the chat. I see. Oh, what have been the biggest challenges in getting engineers that are used to a more traditional approach to embrace these sort of new methodologies?
Good question. We're quite a young team, so we haven't got anyone with a huge amount of baggage, if you put it that way, in that perspective, with regards to how to design parts. Fundamentally, it's always about getting someone on board, right? So we haven't. Those that have a bit more experience haven't seen a problem really. I'm not sure if that answered your question.
I think it did. I think it probably answered the question that Matt was asking. I mean, what you're saying is that it's all about getting people on board to the ideas that you're working with.
Yeah.
And working together on those ideas as well. No doubt you're feeding those ideas back in and improving as you go along.
Exactly. I want to touch up quickly on something you mentioned exactly when we started the question session now. So it's basically challenges in Onshape that we're trying to overcome, right? You mentioned some. I agree it is, but also Onshape is the only cure that we have for this, because you couldn't do the same thing. We wouldn't be able to actually design these parts in any other CAD tool that I know of. At least I know a few. I don't need to name drop them. It's just not fundamentally possible. It's not doable, because we really need to break down the design. And something that I haven't mentioned either is that this whole robot that you saw mentioned or saw snippets of the 600 series, there's a great YouTube video if you want to go and look. Ocado Technology 600 series, and you should find it. It's the bot from a design perspective is actually fundamentally all the way through top-down design. So each and every aspect of the bot we can change with a single master sketch. So there's an interesting and cool way of looking at this from another perspective, even higher level perspective, which is just not fundamentally possible in any other CAD toolbar.
Well, that makes me feel a little bit better.
Yeah.
But in hearing your talk today, it's given me some thoughts about some things that we could do maybe to help make this easier for other people. But
I would be absolutely amazed to see this as like a feature, a function to be able to call within Onshape, right? That's why I talk about it, because it's been so fundamental in the way that we design our robot. So if I'm more than happy to help and try and figure out what a function like this should look like.